Okay, so this week's video I'm going to talk about different types of inhibition. I'm going to go through some problems that have examples of those. And so last week we went through all of this, the Lineweaver-Burke plot and the derivation of the Michaelis-Menten equation, and all of that knowledge should help you understand how the inhibition equations work, you know, what's going on if you look at a graph and you can tell what kind of inhibition it is, those kind of things. So there's three types of inhibition that you need to worry about for this class, and they're competitive, uncompetitive, and non-competitive. And so I'll go in order. So let's talk about competitive. All right. So in competitive inhibition, your inhibitor is going to directly compete with the substrate. That's why it's called that. And it's going to compete to bind the active site. So you've only got one place on the enzyme where the inhibitor or the actual substrate could fit in. So I'll write that down. So okay. Now what that looks like graphically is here's my graph. I've got my substrate concentration here and my velocity here. Let's say that this is what my normal curve looks like, and this is my Vmax. And so if that's my Vmax, my Km is going to be somewhere over here. So we'll call this uninhibited. Now let's say we throw an inhibitor in there. What happens to this graph is it's going to look more like this. So what happens in this case is that Vmax isn't going to change. Vmax is still the same. It's over here. They both reach the same point. But the thing that changes is the Km for this inhibited reaction is all the way over here. It has a higher Km. And the reason that is because the inhibitor is going to prevent some of the substrate from binding to the active site. So Km is going to appear to increase. But as we get closer and closer to higher levels of actual substrate concentration, the high substrate concentration can overcome competitive inhibition. And so when the substrate concentration is much greater than the inhibitor concentration, the enzyme is much more likely to bind the substrate than the inhibitor. So the main takeaway from this is that this competitive inhibition is only going to affect Km. Vmax and Kcat are unchanged. Just always keep that in mind for competitive inhibition. So the Michaelis-Menten equation for a competitive inhibition reaction, it's going to take the form of V naught is going to be equal to Vmax times the substrate. That all looks the same. And then you've got this term alpha. Alpha is going to modify the Km term because if you remember from what we just did up here, we know that competitive inhibition only affects Km. So this alpha tells us to what degree the competitive inhibitor is affecting Km. So alpha is a factor that makes Km appear larger. And so the value of alpha is the degree of inhibition, and it depends on that inhibitor's concentration, and it depends on the affinity for the enzyme. And so if you'll remember, this is also a useful equation to know that, alpha is equal to 1 plus the inhibitor concentration over the Ki, where Ki is the Kd for the enzyme inhibitor complex. So Ki is the Kd for an enzyme inhibitor complex. And we treat that kind of the same as we do, like it follows the same logic that, an enzyme substrate complex dissociating back into an enzyme and a substrate logic follows. It's like that. And so if we want to like see what this looks like in a Lineweaver-Burke form, we can say that we'll do our reciprocal thing. So this becomes 1 over V naught is going to be equal to alpha times Km plus the substrate over Vmax times the substrate. So we'll get 1 over V naught is equal to alpha times Km over Vmax times S plus the substrate over Vmax times the substrate again. These cancel out. We're left with 1 over V naught. It's going to be equal to alpha times Km over Vmax times 1 over the substrate plus 1 over Vmax. So what that tells us is that our y-intercept, it's going to stay the same. It's going to be, as our normal equation, it's going to be 1 over Vmax. Our x-intercept is going to change, though, because we're modifying, this slope term. So if we do all that math out, we'll get our x-intercept at negative 1 over alpha times Km, which should make sense because our x-intercept in the normal Lineweaver-Burke equation is going to be negative 1 over Km, and so that alpha term is just going to be modifying that Km. All right. And so, I was going to draw the graph. So, okay. If we look at a graph of this. So if I'm drawing just my normal Lineweaver-Burke equation, I'll have, my 1 over Vmax, my negative 1 over Km here, and then I'll just have some slope of Km over Vmax. All right. Now the alpha term is going to make the Km term appear bigger. So what that means is that instead of going farther out on the x-intercept, negative 1 over alpha times Km would be closer to the origin. So it'd be somewhere around here. So negative 1 over alpha Km would look like that. Vmax stays the same. So it's still going to intersect the y-axis at the same point, and it's going to make the slope steeper because we have that Km term being modified by alpha. So the slope here is going to be alpha times Km over Vmax. And that should make sense because alpha is going to make this bigger, so the slope should be greater. All right, so that's how that works. Oh, and the axes here are, of course, 1 over the substrate concentration and then 1 over V naught. Okay, now this competitive inhibition does not affect Vmax, but some types of inhibitors can. And so uncompetitive inhibition is one of those examples. And so for uncompetitive, Okay. So the inhibitor binds to the enzyme substrate complex. And we usually see this with multi-substrate reactions. And so the way that this is going to work is that V naught is going to be equal to V max times S over Km. Km is unchanged here. Times this alpha prime term now that modifies the substrate concentration. And so we have a similar formula for the concentration that can be represented as alpha prime is equal to 1 times, or 1 plus the inhibitor concentration times, or over Ki prime. And so if we're looking at what this would look like as a Lineweaver-Burke equation, we'd take the reciprocal, we'd say 1 over V naught is equal to Km plus alpha prime times the substrate concentration over V max times the substrate. And we'll get 1 over V naught is equal to Km over V max times the substrate plus alpha prime times the substrate over V max times the substrate concentration. So these will cancel out. We're left with 1 over V naught is equal to Km over V max times 1 over the substrate concentration plus alpha prime over V max. All right, so what that means is that now our y-intercept, that's going to be at alpha prime over V max instead of just 1 over V max. And our x-intercept, if we do the math out, we'll get negative alpha prime over Km. And so what this is going to look like is you'll have a normal Michaelis-Menten plot that looks like this. Oops. Okay, so here's my V naught and my substrate concentration. So here's V max. And so this is V max with no inhibitor. But when I add the inhibitor in there, because Km stayed the same, the first part of this slope is going to look the same. So it'll come up here, but then it'll split off, and we'll have our Vmax, or our apparent Vmax with the inhibitor. All right, and so what this looks like in a Lineweaver-Burke form. So 1 over V naught over here, 1 over the substrate over here. So normally we'd have 1 over V max, we'd have negative 1 over Km, and a slope of V max over Km. Or I'm sorry, Km over V max. Now, when we inhibit it, what's going to happen is we changed our y-intercept and our x-intercept. So our y-intercept is going to be higher up. So it's going to be, let's say over here, we'll have alpha prime over Vmax. And then negative alpha prime over Km as our x-intercept, which is going to go farther away. And these should have the same slope. it would actually be like over here to make them have the same slope, but that's just me drawing it fairly poorly. Just keep in mind that these should have the same slope because the slope stays the same as Km over Vmax. It should actually look like two lines like this. Just keep that in mind. Now the last type is competitive inhibition, or I'm sorry, non-competitive inhibition, which is also called mixed inhibition sometimes. And this is the one that I would say that you have to worry kind of the least about. Like, I'm not going to go into like how the graphs look or how to, derive the equations and all that stuff, because it's basically the same thing as what we've been doing. And also the MCAT and Dr. Sims define them sort of differently, and you have to keep the two straight in your head. So I don't want to make it too complicated with how I explain it. But just the important things to remember here are that for non-competitive inhibition, your equation, that's going to be V naught is going to be equal to Vmax times the substrate concentration over, and then we use both alpha and alpha prime, because the thing is that for a non-competitive reaction, you can affect both the slope and the y-intercept, because the inhibitor itself can bind both to the active site or the enzyme substrate complex. So it's kind of, that's one of the reasons it's called mixed inhibition, because it's kind of like a combination of uncompetitive and competitive, in the sense that it has a choice where it wants to bind. So we use both alpha terms. So we have alpha times Km plus alpha prime times the substrate concentration. And so when we do our double reciprocal, we'll get 1 over V naught is equal to alpha times Km over Vmax times 1 over the substrate concentration plus alpha prime over Vmax. And so the thing about this to keep in mind is that this is going to affect both slope and y-intercept. And so the degree to which it does that depends on, the values of alpha and alpha prime. And so that's pretty much all I wanted to talk about for just the inhibition types. And I'm going to pull up some of the problems here from the Action Center.